press the accelerator in an electric car and the vehicle moves almost instantly. There is no engine waiting to build speed, no clutch changing gears, and no explosion under the hood. Electricity becomes wheel movement in a fraction of a second. But how does energy stored in a silent battery actually move a 2-ton car? The journey begins in the traction battery, usually mounted under the floor. Think of it as a large rechargeable energy tank made from thousands of individual battery cells. The pack stores electrical energy as direct current, or DC. A battery management system constantly watches the pack. It checks temperature, voltage, and state of charge and protects the cells from being charged or drained too far. A cooling and heating system also helps keep the battery inside a safe operating range. When you press the accelerator, you are not directly opening a flow of electricity like a water tap. You are sending a request to the car's computer. The power electronics then decide how much energy the motor should receive. In most modern electric cars, an inverter converts the battery's DC electricity into carefully controlled alternating current, or AC, for the traction motor. By changing the timing and strength of that current, the inverter controls motor speed and torque. Inside the motor are two main parts, a stationary section called the stator and a rotating section called the rotor. Electricity flowing through coils in the stator creates a rotating magnetic field. That magnetic field pulls or pushes the rotor around, depending on the motor design. The spinning rotor produces torque, the twisting force that moves the car. A reduction gear then slows the motor's very fast rotation and increases the useful twisting force sent to the wheels. Most electric cars use a single-speed reduction gearbox because an electric motor can work efficiently across a much wider speed range than a gasoline engine. A few vehicles use more than one gear, but they are the exception. This is why an electric car can accelerate smoothly from a standstill without changing through a long series of gears. Charging works in the opposite direction. At home or at many public chargers, the car receives AC electricity. An onboard charger converts it into DC before storing it in the battery. A DC fast charger supplies DC power directly to the battery system, so it can charge much faster. Then comes one of the cleverest parts, regenerative braking. When you lift off the accelerator or press the brake gently, the wheels can turn the motor instead of the motor turning the wheels. The motor now behaves like a generator. It converts some of the car's motion back into electrical energy, and the power electronics send that energy into the battery. The resistance created by generating electricity also slows the car. But regeneration cannot recover all the energy. Some is lost through heat, air resistance, tires, and electrical conversion. The car may also use ordinary friction brakes during hard stops, at very low speeds, or when the battery is too full or too cold to accept much energy. So an electric car is not simply a battery connected to wheels. It is a fast conversation between the battery, computers, inverter, motor, gearbox, and brakes, repeated thousands of times every second. And that is how silent electricity becomes motion, then briefly turns back into electricity when the car slows down.